So this is our final topic for today, and I'm going to work through one final example. So the final thing that we want to look at is finding global max and mins on a bounded set. So previously, this is the exact same function that we saw in the last example. Only now I want to look at when is this function highest and lowest when I'm looking at just a very narrow part of the domain. That I want to know, if I look at this triangle, the triangle with vertices 0, 0, 1, 0, and 1, 1, when is my function highest and when is my function lowest? So looking at a picture of this in the xy plane, I'm looking at the triangle with vertices 0, 0, vertex 1, 0, and vertex 1, 1. I shouldn't be standing on this side, sorry. And I don't exactly know what this function looks like right now, but I don't have to worry about what this function looks like right now. What I do know is that it's some crazy curvy sheet thing that's curving upwards and downwards and has some crazy saddle points and stuff. And I'm bounding this to just look at the place right here where I have the point 1, 1. And so I'm essentially cutting this triangle in the xy plane, and I'm trying to say, on this triangle up here in space, what are the highest and the lowest points on this sheet of this triangle up in space of this three-dimensional function? This graph isn't very helpful, I understand. It doesn't look very helpful for me either. But how can I find out where this graph is highest and where this graph is lowest? There are 3 steps that we're going to do. The first step is to find the critical points of our function f of x, y that lie in the triangular domain. And we already did this step, so this is nice. Some of our work is saved for us. So last time we found that we had 3 critical points. We had a minimum value at 0, 0. We had a saddle point at square root 2, 1/2. And we had another saddle point at square root 2, negative square root 2, 1/2. But notice that square root 2 is at about 1.4. So this square root 2, 1/2 point, I'll draw it in green, it lies outside of our domain. And our negative square root 2, 1/2 clearly lies outside our domain. So it turns out we aren't going to have to worry about those points. We just have this one critical point that we found last time. It turns out it's that corner point. So that's the first step, and we're already done. And I'm just going to collect my critical points. I'm going to put them up here in the corner where I won't forget about them. So we found one potential max-min value. That's one of them. And we can move on to step 2. Step 2 is to find the critical points that lie along the straight line boundaries. Find the critical points, step 2, along the boundaries. So what do I mean by that? We know that this function, along each of its edges, that's a key place where it might go up or go down because we're cutting it right at that place. And along this line, somewhere along this edge, it might have a really high value or a really low value. So let's go ahead and evaluate the critical points along the boundaries. We have to do it boundary by boundary. So first, my first step is to look along this bottom line. So the bottom line, that has the function, this is the line where y is exactly equal to 0. So algebraically, I go into my function and I plug in f of x comma 0, plugging in 0 for y, and I get x squared, 0 for y, this term becomes 0, this term becomes 0, and this term becomes 4. And I want to know what are the critical points along this boundary. So I'm going to take the derivative of this function, and notice that it's easy to take the derivative of it in this case. It's really only a single variable function. So the derivative of this function with respect to x is going to be, the derivative here is 2x. So when is this equal to 0? This is equal to 0 when x is equal to 0. Notice that this gives us the same point that we found before. This is the point where x is equal to 0, and we already assumed that y was equal to 0. So we found that this point is a critical point along this line. Great. It's not very helpful information necessarily, but it rules out that any points somewhere else along the line might be critical points. Next, I'm going to check the vertical boundary. I don't know how to spell vertical. It's okay. So the vertical boundary is going to be this line right here. This line has the equation, it's when x is exactly equal to 1. So I'm going to go into this function, and I'm going to let x be equal to 1. So I'm looking at the function f of 1y. When x equals 1, I get 1 squared plus 4y squared minus 2 times 1 times y plus 4. And I want to know what are the critical points along this boundary, so I need to take the derivative of this and set it equal to 0. So when I take the derivative of this, I'll just write f prime of y. It's a function of y in this case. My derivative, my constants are going to disappear, and my derivative becomes 8y minus 2. A critical point, I take the derivative, then I set it equal to 0, and I find that when y is equal to 1/4, I get a critical point. So what does that mean here? That means when x is equal to 1 and y is equal to 1/4, that's a critical point along this boundary. So I'm going to list that up on my list. We found a new point. It's the critical point when x is equal to 1, when y is equal to 1/4. So that's another potential max or min value that's a critical point along this boundary. And I'll label it right here in green. This is the point 1/1/4. So we've done 2 of the different boundaries. We have one more boundary along which I'm going to find the critical points. This final boundary is going to be the boundary along the line, and in this case, this is the line where y is equal to x. So I'm going to plug y equal to x into my function. So I'm looking at the function f of x, because y is equal to x. So anywhere I see a y, I'm going to turn it into an x, and I get x squared plus 4x squared minus 2x squared times x plus 4. I'm going to simplify this a little bit. It looks like I have 5x squareds, and then I have minus 2x cubed, and then I have plus 4. So this is my function. Now it's a function just in terms of x's. I should probably relabel it. I'll call it h of x. It's just a function in terms of x's. I'm going to take the derivative of this function because I want to find the critical points. I take the derivative and set it equal to 0. So what's the derivative of this function? It's 10x minus 6x squared, and that constant becomes 0. So I'm going to take the derivative and set it equal to 0. How do I solve? I need to solve for x. For when this is equal to 0, I can factor out an x, and I get 10 minus 6x equals 0. I'm going to pause for a second. This is a technique that we've seen a couple of times, that this repeated x in this polynomial, it's easy to factor this out. That's something that will happen commonly, in part because it's common to have critical points where x equals 0. So what does this tell me? This is going to be equal to 0 when x equals 0. But that's boring because we already have when x is equal to 0, that gives me the point x equals 0 and y equals 0, which is 0, 0, which is the point that we already found, the point along this line where x is equal to 0. Boring. It also gives us the point where 10 is equal to 6x. So I divide both sides by 6, and I get 5/3 is equal to x. Interesting point. This is a new point, right? This is the point where x is equal to 5/3, and because we know that we're along this line, it's going to be the point where y is also equal to 5/3. Interesting new point, but alas, it's outside of our triangle. 5/3 is bigger than 1. So we just found another point that's a critical point that's way out here. That's not in our domain, so we don't really care about it. Step 2 is complete. We now can move on to step 3. Step 3, we're going to find the heights of all corners, I guess I should call them vertices, and critical points. So we've narrowed our list down to these 2 points that are critical points that may or may not be high or low points on this graph. But we also have to evaluate all of the endpoints, because let's say this line is just increasing and increasing and increasing and it gets chopped off right at 1, 1. We want to make sure what is the highest point along that line. It's going to be at the point 1, 1. It's not a critical point, but it would be the highest point because it's the end of that line segment. So let's go ahead and evaluate this. That means that we're going to look at what is f of 0, 0. Our function evaluated at the point 0, 0 gives us a value of 4. What is f of our second critical point? 1, 1/4. That's equal to 1 plus 4 times a 4th squared minus 2 times 1 squared times a 4th plus 4. I can do some arithmetic because I'm so good at arithmetic, and I end up with 1 plus 4/16. 4/16 is just a 4th. So it's 1 plus a 4th minus 2/4 plus 4. 4 is 16/4. And I can convert this into 4/4. So how many fourths do I have? I have 5/4. I get 19/4. Right? Maybe. Minus 2/4. Yes, I feel okay about that. I also have to plug in my corner points. So I'm looking at the corner point 0, 1. That's this corner right here. Plugging in 1 for x and 0 for y, I just get 1 plus 4, which is equal to 5. And finally, plugging in the corner point 1, 1, I get 1 plus 4 minus 2 plus 4, which is equal to 7. And we're done! Hooray! Why are we done? So we just found out the heights at each of these crazy places. And I'm going to label these heights in red. No, in blue. Here, I have a blue marker. So looking at our triangle, we just found that our height down here at 0, 0 is 4 high. We found that our height down at our next corner, 1, 0, right here, it's 5 high. Up at 1, 1, it's 7 high. These are our functional outputs. And at our crazy saddle point, it's 19/4 high, which is 4 1/4, right? No, 4 3/4. So I'll write that as 4 3/4. So now we just need to pick what are the highest and the lowest points. We see that up here at 1, 1, that's our max value because it's highest, and down here at 0, 0, that's our min value because it's lowest. Well, why did we go through all that work to find this saddle point if it didn't end up being anything interesting? It turns out it actually is interesting. We see that this is up here at a height of 5, and this is up here at a height of 7, but in between we're swooping down before we swoop up again. So this is a saddle point that's actually the minimum along this vertical line, and it's a minimum value along the line. It's just not a minimum value of the graph because it doesn't actually get lower than the 0, 0 point right at the origin. That's it. Thank you so much. I realize that we introduced a lot of techniques and there's a lot of algebra that goes along with these techniques, but I do think that it is cool stuff. We're doing really relatable geometric cool stuff. Thanks.